All right. So in this video, we're going to take a look at some of the examples from this week's ALEKS topics. And this week, we're going through the periodic table, taking a look at bonding and matter and energy. So the first question up here looks at how the periodic table is organized. And as a quick reminder, this periodic table that's shown here on the left is the one that you will be provided with when you take an exam or a quiz. So you can print this out and you can have it with you as you take your weekly quiz or as you take your exam. You want to make sure, however, that you don't have it colored in or you have any other marks on it. It needs to be in this form when you start your quiz or your exam, which means you need to be able to interpret the different parts of the periodic table and be able to find things and locate the elements based on how the table is organized. So the first couple of questions here, it's asking us to, they give us some descriptions, and it says, does any element with Z less than or equal to 92 match the descriptions? Remember, Z is the atomic number, which on our periodic table is a number at the top of the box. That's the number of protons that we're looking at. So 94 or less would be, that's plutonium, and lower, we're not looking really at the heavier elements. All right, so we'll take a look at a couple of these, maybe the first two up here. So it says an element in period 1 and group 2A. So period 1 is the first row. The period is the row on the periodic table. So our first period here would be this one. That's period 1. And that right away we've limited ourselves to see if I can zoom out a little bit, this first row over here. So in the first row, we only have two elements, hydrogen and helium. Hydrogen's in 1A, helium's in 8A. So obviously now there isn't any element in group 2A that would satisfy this. All right, so then the answer there would be no. And the second one, it says a non-metal in group 6A. So we locate group 6A. That's this column here. So the groups are the same as the columns. And we're looking for a non-metal. So the non-metals are found generally on the right side of the periodic table. And you can select any of these: oxygen, sulfur, selenium, tellurium, etc. Well, you want to pay close attention, actually, because as you go down, you do encounter your metalloids down here. So oxygen, sulfur, selenium would be options. So if you checked yes, which you should for here, give the symbol of the element, and then you can put uppercase O, uppercase S for that. So that's the way you want to navigate that first question of the organization of the periodic table. All right, the second one looks at isotopes. And isotopes, remember, are different forms of the same elements of the same element. What makes them different, or what's makes them the same element in the first place, is that they have the same number of protons. But they have different number of neutrons, which then would make their mass numbers different. Right? That's how we define our isotopes. So it says how many protons and neutrons are in an atom of nickel-61. So this notation is one of the notations that's used to represent different isotopes. So this here tells us a couple things. Obviously, Ni means nickel. Maybe not obviously, because you're still getting used to the periodic table, but you can look it up on yours. So nickel, whereas nickel's right here. And then the 61 here is actually telling you the mass number for this particular isotope of nickel. Okay, so what does the mass number tell us? Well, the mass number is the sum of the protons plus the neutrons. So if we know that this thing is nickel, then we already know the number of protons. The protons is the atomic number, in this case for nickel. And guess where we can find that? We can look it up on the table, in the PT's periodic table. So you don't need to memorize the numbers on the periodic table, right? You always have a periodic table available. You just need to be able to interpret it. Nickel is right here. The atomic number in this case is 28. That's the number of protons. That's the same as the atomic number. So 28 is what we're looking at. So now we know, according to our simple math that we're doing, okay, so the mass number is equal to the sum of the protons plus the neutrons. The mass number we were given as 61. The number of protons we just found from the periodic table, because how do we know that it's 28? Because we're told that it's nickel and it has to be 28, which means we don't know what the number of neutrons are, right? We need to calculate this, and this becomes a simple mathematical operation. We need to rearrange our equation so we can take away the 28 from both sides, and we end up with the number of neutrons left on the right side. So 61 minus 28 gives whatever that is, right? So that would be 33, would be the number of neutrons. Okay, so the math here that's involved is fairly straightforward. Maybe what the most challenging thing is this relationship, right? So the mass number being the sum of the protons and neutrons, and the number of protons you can find always from the periodic table, as long as you know what element it is that you're dealing with. All right, the third question here looks at naming binary ionic compounds. So binary just means made up of two components. And then ionic means that ions are involved. Okay, and ions are things that are charged, meaning they have a positive or negative charges. And generally in ionic compounds, we're going to see metals and non-metals. Right, those are the two components. The metals form positive ions, and the non-metals form negative ions. And as a result, when you have positive and negative opposite charges attract, that's what the ionic bond is that keeps these ionic compounds together. So let's take a look here at the first one. So it says, fill in the name and the empirical formula of each ionic compound. The empirical formula is nothing more than the simplest whole number ratio. So the simplest or the smallest. Whole number ratio of the elements or the ions in the compound. Okay, and when we combine ions together to make compounds, those ratios are written as subscripts after the symbol for the element. So let's take a look at a couple of these. We'll do the first two. All right, so we have copper, it says the cation, which is the positive ion. That's the name that we give to positive ions. and then the negative ions is called an anion. So our cation here is Cu plus. Remember, plus is the same as plus 1. We don't normally put a 1 in, it's understood. And then the Br minus is the anion. Again, that's the same as negative 1. So we need to combine these in a ratio so that the charges cancel. So obviously now a plus 1 and a negative 1 will cancel out. So these are going to combine in a 1-to-1 ratio, right? We always put the cation first and the anion second, and we put the ratio now as subscripts. We don't need ones. Okay, ones are understood. So this then just becomes CuBr as your empirical formula. 1-to-1 is the smallest ratio, smallest whole number ratio possible. That's your empirical formula. And then the name for these binary ionic compounds, we name the cation first. So Cu is copper. And then the Br minus, Br itself is bromine. But as a last name, we change it to bromide, the IDE. And with the nomenclature or the naming, we'll notice that we have copper in there. Copper is an example of one of the metals that's found right here in the middle of the periodic table. That's a transition metal. Copper is right here, which means that they can have variable or different charges. And if that's the case, we need to specify the charge on the copper ion. Well, we were told that it was copper 1 plus, so we put the charge right after it in parentheses as Roman numerals. So that's a Roman numeral for 1. It's I. And we need that there because we're looking at copper, which is a transition or variable charge metal. So copper 1 bromide. If we take a look at the one underneath it, so copper 2 plus and Br minus, we'll see that they're going to share things that are common. All right, so we have again copper and as the cation, so we put that first. Br as the anion, we put that second. The copper is 2 plus. The bromide here is 1 minus. So we would need 2 bromides to give us negative 2 in order to cancel out the 2 plus, right? So that's where the subscript 2 comes in. We only need the 1 copper, so we don't need to put the 1 in as a subscript. So this is our empirical formula. The name again, we have copper first, so we write that. That's the metal's name goes first. Br as a last name, again, is bromide. Okay, the 2 here, in terms of the name, there's nothing in the name for ionic compounds that tell us this is 2. However, now, again, just like above, where we specified the charge on the copper being 1 plus, here now the charge on the copper is 2 plus. So we need to say the charge there is 2. We use the Roman numerals in parentheses. So that's copper II in parentheses, copper 2 bromide as the name for that compound. All right, and you want to continue the rest along the same vein. The next question looks at some of the ionic compounds that have polyatomic ions in them. Okay, so the ones that we just did were binary ionic compounds. Some ionic compounds are made up of polyatomic ions, which are just collections of atoms that have charges. So I'll take a look here at the first one. So we have Ca 2 plus, and we have OH minus. All right, so now you'll see that the OH minus, this actually has 2 atoms that together now have a charge of -1, right? So this -1 charge here is associated with this entire thing, with the OH. And that's important because when we start looking at our subscripts, we need to include that in our in the name or in the formula. So we're going to do this the same way. So we're going to write the metal first. So we have calcium, and then we have hydroxide, OH. Okay, so now we can see that the 2 plus and the 1 minus don't cancel out, right? We actually need two minuses. We need two minuses to cancel out 2 plus. So we actually need two hydroxides, two OHs. So the way now we would write that is if we have a polyatomic ion and we need more than one of it to cancel out charge, we put that polyatomic ion in parentheses and we put the 2 right after it. So this tells us we have two OHs to cancel out the 2 plus from the hydroxide, from the calcium, the Ca. So now when we name this, Ca is calcium, we name the metal first, and then the anion comes second. So OH, you need to know that one, that's hydroxide. Okay, and as you're getting used to these, I would suggest, because you're probably not going to memorize your polyatomic ions really quickly, but you need to know several of them, and they're outlined in the videos. Okay, look these up from the textbook as you are doing the ALEKS homework. Okay, because you'll see, and again, the point of ALEKS is to give you practice, putting these together, and also with the naming. So you may see a couple polyatomic ions, for example, the ClO2 minus. That's not on the list of ones that I need you to memorize, but the idea behind that one is that you can still use the same process to put the ionic compound together. So you can look these up, whichever ones you don't know, you can look them up in your text. When you watch the pre-recorded videos, you'll see I'll give you an exact list. I think there's 10 or 11 polyatomics that you need to memorize absolutely for your quiz or your exam. But as you're doing your ALEKS topics, right, you can look things up in your textbook always as you go, because the point of ALEKS is to give you practice, to have help the material sink in. All right, the next one here looks at predicting the ions formed by the main group elements. So let's take a look here at a couple of these. So we'll do chlorine, Cl, and we'll do magnesium. Well, it doesn't give you the symbol, so let's write it out. So chlorine and magnesium. So the first thing you want to do is to locate these on the periodic table, because this will tell you whether these are going to form cations or anions generally. So chlorine, if we go up to our table, we'll see that chlorine is here on the right side of the table. And on the right side, we find nonmetals, and nonmetals tend to gain electrons to form anions. All right, so chlorine, Cl, will form a negative ion, which would be an anion. Nonmetals want to gain electrons, and that's the reason for that. What will be the charge on the chlorine? Well, there's a quick way we can figure this out. So if this is chlorine here, chlorine is in group 7. Okay, and the way that we figure that out for the nonmetals is we take the group number and we subtract 8 from it. So the charge then becomes Cl minus, right? 7 minus 8 is minus 1. And obviously with a negative charge, that would make it an anion. Magnesium, same thing. We find it on the periodic table. Magnesium's here on the left side. It's a metal. Metals tend to lose electrons to form positive charges. And for the metals, okay, for the main group metals, the charge is simply equal to the group number. Magnesium's in group 2, so the charge there is 2 plus. And it's fairly simple for those just to locate them and to identify their charges. And this then would be obviously a cation, which is a positively charged ion. All right, and then the next one we'll take a look at here looks at classifying each of the chemical compound as ionic or molecular. Okay, so the quick way to identify these are your ionic compounds will contain what you need to look for, either metals, or polyatomic ions. And for molecular compounds, or sometimes they're referred to as covalent, you'll see only nonmetals. Okay, so that's what we're looking for. So for example, in the first one, you see there's HN3. Right? All of these are non-metals, and none of these are polyatomic ions, so this would be molecular. And let's look at the third one. You'll see that we have iron in here. Iron is a metal, so that tells us it's going to be ionic. You also see that this thing in parentheses. That tells us it's a polyatomic ion. That confirms that it is ionic as well. Let's jump down to the next table down here, where it gives you the formula for an ionic compound, and it asks you to identify what the cation and what the anion is for these. So let's take a look at the next ones. We have V2CO3 3 times. All right, so you're told explicitly that these are ionic compounds, so we know that there are ions involved. So what are these ions? Well, the parentheses here actually tell you that we're dealing with a polyatomic CO3, right? The thing in parentheses is a polyatomic ion. That's the carbonate, and the carbonate itself has a charge of 2 minus, right? That's one of the polyatomic ions you need to know. That's on your list. So that's one of the ions. That's the negatively charged. So that would be your anion involved in this case. And then we also need to identify the cation, which in this case would be V, vanadium, and we need to know the charge on it, right? So what's the charge on the vanadium ion in this compound? Well, we don't know what it is. We can look at the anion involved. So we know that that carbonate is 2 minus, and we have 3 carbonates in the formula, right? So if we times this by 3, because that's how many we have, 3 times the charge there gives us 6 minus for the overall negative charge. Now, that has to be balanced out by the 2 vanadiums, right? So 2 vanadiums here should give 6 plus to cancel out that total negative charge, which means then that 1 vanadium, which is what we're looking for, would have a charge of 3 plus. So the ion here would be V3 plus as your cation. Okay, there's another way we can quickly determine this. Once we identify that this is made up of V and CO3, we can take our formula that we're provided with, and the subscripts become the subscripts for the in this case the anion becomes the charge for the cation. The subscript for the cation becomes the charge for the anion, right? That's the reverse of the cross-charge method that you learned. That's in one of the videos that shows you how to put an ionic compound together in the first place. This is just going backwards. It's a quick way to determine the charges of the ions. All right, the next question here looks at, where are we now? Molecular compounds. And in contrast to the ionic compounds, the molecular compounds, which again are also known as covalent compounds, are a lot simpler to navigate in terms of their nomenclature and their formulas, because with these, we're going to use prefixes and these tell us the number of each atoms in the compound. Okay, and for molecular covalent compounds, we're only going to see nonmetals. So the first one here, let's actually do the second one. It says dinitrogen tetrafluoride. Okay, and remember in the ionic examples that we did, we never saw the prefixes, right? That's one big difference between ionic and covalent, or ionic and molecular. So the first thing here is we have dinitrogen, nitrogen, that's nitrogen is N, and then tetrafluoride. Fluoride comes from fluorine, which is F. So those are the two elements involved. The di here tells us that we have two nitrogens, so N2, and then the tetra tells us that we have four fluorines. So N2, F4. It is that simple for your covalent or for your molecular compounds. You need to know, however, your prefixes. All right. Let's take a look at the next one. So here we're going back to ionic compounds. It says to deduce the empirical formula from its name. All right, so let's take a look at the first one. So it says nickel 2 bromide. And again, this is ionic. It's ionic because we have a metal in there. The first part of the name actually tells you something very important. It tells us that we have nickel, and the 2 here tells us the charge on the nickel is 2 plus. Bromide is Br with a charge on it. What's the charge on bromide? Well, find bromide or bromine on the periodic table. Bromine is here in group 7. If it's in group 7, the charge on the ion should be the same as chlorine has, because chlorine is in the same group. So the charge there should be -1 on the bromide. We've seen the bromide before as well. So -1. And then when we put the formula together, we can do our cross-charge thing. The 1 here on the bromide becomes a subscript on the nickel. The 2 on the nickel becomes a subscript on the bromide. And then we clean up our formula. We can omit the 1s because 1 is understood, so we only need the 2 for the Br. All right, the next one we're looking at here is predicting the compound formed by 2 main group elements. All right, so we'll take a look at, so then we're given each of the elements, element 1, element 2, and then we need to say whether it's ionic, molecular, or neither, and then if it's either ionic or molecular, we need to say what the formula is going to be. All right, so we have sulfur and we have sodium. So S and sodium is Na. So sulfur, if you look on the periodic table, is a nonmetal. Sodium is a metal. So right away now, go back to what we talked about before. We have a metal and a nonmetal. This tells us that it is going to be ionic. And when we put these together, remember you always put the metal first, or the cation first. So we have Na and we have S. What are the charges involved? Well, sodium's in group 1 when you look on the periodic table, so it would be 1 plus or plus 1. Sulfur is in group 6, so 6 minus 8 gives -2 or 2 minus. So we put these together, we do our cross charge. The 1 on the sodium becomes a subscript on the sulfur. The 2 on the sulfur becomes a subscript on the sodium. And then we clean it up. We have Na2S. We don't need the 1 for the subscript, so Na2S would be our formula.